friends, welcome to 6th and last lecture of class 11th chemistry chapter 2 structure of atom. This lecture is a continuation of quantum numbers video. In this lecture, we shall discuss the rules for filling electrons in orbitals. So there are three important principles which are used for filling the electrons. These are Aufbau principle, Pauli's exclusion rule and Hund's rule. So let's discuss each of them one by one in detail. First, Aufbau principle. This principle states that orbitals are filled in the order of their increasing energies. This means that electrons first occupy the lowest energy orbital available to them and then enter the higher energy orbital only when the lower energy orbital are filled. So always the lower energy orbital is given preference by the electrons to get filled first, and only after it is filled completely then the electrons will go to the higher energy orbitals. So for filling the electrons we must know the energy order of the orbitals. So for finding out that which orbital has lower energy, we have few rules. So the lower the value of n plus L for an orbital, the lower its energy. So in the previous lecture we have studied about quantum numbers and we have studied about n, that is principal quantum number, and L, that is azimuthal quantum number. So lower the value of principal quantum number plus azimuthal quantum number, the lower the energy of orbital. So let's understand this by taking an example. So let's take two orbitals, that are 1s orbital and 2s orbital. So for 1s orbital, you know that let's find out the value of n plus n. So you know that for 1s orbital the value of n is 1 and value of L is 0. So n plus L becomes 1 plus 0, that is 1. And for 2s orbital value of n is 2 and value of L is 0. So n plus L becomes 2. So in this you can see that the n plus L of 1s orbital is coming as lower. So this means that the energy of 1s orbital will be lesser than the energy of 2s orbital. So 1s orbital will be filled first and then afterwards the 2s orbital will be filled. Now if two orbitals have the same value of n plus L, then the orbital with lower value of n will have lower energy. So sometimes we get a question in which both the orbitals are having same value of n plus L. So for example, the orbitals 2p and 3s are having same value of n plus L, that is 3, because in 2p we are getting n plus L as 2 plus 1 and in 3s we are getting n plus L as 3 plus 0. Both of them are coming out to be same. In such a case, the orbital with lower value of n will have lower energy and will be filled first. So in this you can see that 2p is having lower value of n than 3s. So thus 2p will have lesser energy and will be filled first. So both of these rules are important for determining the energies of orbitals. So by applying the n plus L rule, we can find out the energy order of all the orbitals. So electrons are filled in this order: 1s, 2s, 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 4f, and finally 5d. So this is the entire series in which the electrons will be filled. Now there is an easy trick to remember this series. So first write the names of all the orbitals like this, as I have shown you in this diagram. Now starting from the top, the direction of arrows will give the order of filling the orbitals. So here you can see that I have put arrows and the direction of arrows will give the order of filling the orbitals. And anytime you get confused that which orbital will be filled first, then apply the n plus L rule and find out that which orbital is having lower energy, and the orbital which will be having lower energy, it will be filled first. Now the second rule is Pauli's exclusion principle. This rule states that no two electrons in an atom can have the same set of the 4 quantum numbers. So all the 4 quantum numbers of any two electrons cannot be same. Only two electrons can exist in the same orbital, and these electrons must have opposite spin. So this means that the maximum number of orbitals possible in a single orbital is 2. This means that no more than 2 electrons can come in one orbital. Now I have already told you that 2 electrons will come in one orbital in the 5th lecture. But Pauli's exclusion principle is the formal way which stated that no more than 2 electrons can come in one orbital. Third, Hund's rule. This rule states that pairing of electrons in the orbitals belonging to the same subshell doesn't take place until each orbital in that subshell has got one electron each. Now let's understand this with the help of an example. So basically, Hund's rule says that the pairing of electrons in the orbital belonging to the same subshell will not take place until each orbital of that subshell will have one electron each. Let's understand this with the help of an example. So here you can see that we have 3 electrons and we have to arrange them in a subshell, that is p subshell. So p subshell has 3 orbitals. In each orbital there can be 2 electrons at the max. So there is the first electron in this first orbital and second electron in second orbital. Now we have to arrange the third orbital. So where we will place it? This is given by Hund's rule. Can we place it in the first orbital? No. Can we place it in the second orbital? No. Why? Because the pairing of electrons will not take place until all the orbitals are filled, or have one electron each. So as this third orbital is not having one electron, it is empty, that's why the pairing cannot take place. So this electron has to go into the third orbital according to Hund's rule. Now if we bring a fourth electron, then that can go into any of these orbitals because all of them are having one electron each. So after they are having one electron each, we can do pairing in the orbitals. So I hope that Hund's rule is clear. Now let's discuss that how by applying all these 3 rules we can find out the electronic configuration of atoms. So the distribution of electrons in orbitals of an atom is called electronic configuration. After learning all these 3 rules, we can easily find the electronic configuration of any atom. Now to represent electronic configuration, we have a standard method. That is, we represent it by NLX, in which N is the shell number, L is the subshell name, and X is number of electrons. So let's take an example. Let's take the example of the orbital 2p5. So in this, 2 is the shell number, p is the subshell name, and 5 is the number of electrons in that subshell. Now let's practice writing the electronic configuration of few elements. The first element is hydrogen and it has 1 electron. So the first electron will obviously go into the lowest energy orbital, and that is 1s orbital. So to represent that 1s orbital, we will draw it. We will draw a square, and this is 1s orbital. And in that, to represent electron, we will draw this arrow symbol. So this means that there is 1 electron in 1s orbital, and this can be written as 1s1. Now this is because, as I have told you before, that for writing the electronic configuration, it has 3 parts: N, L and X. So N is the shell number. You can see that this here we are putting the electron in the first shell, that is K shell. So N is equals to 1. L is the subshell name, that is S subshell, and 1 is the number, X is the number of electrons in that subshell. So you can see that there is only 1 electron, so that's why we are writing 1s1. So this is the electronic configuration of hydrogen. So now let's write the electronic configuration of oxygen. It has 8 electrons. So first we will put the electrons in 1s orbital. So 1s orbital, and as it has capacity of 2 electrons, so here we will put 2 electrons in 1s orbital. Now 6 electrons are left. So which is the next orbital in energy order? That is 2s orbital. So again we will put 2 electrons in 2s orbital. And now which is the next orbital in the energy order? That is 2p orbitals. So therefore, now in 2p subshell there are 3 orbitals. So that's why we have drawn 3 2p orbitals. Now, as we have to fill only 4 electrons, we are left with only 4 electrons. So that's why this 2p orbital will not be completely filled. So it will have 4 electrons. And we have arranged the electrons according to Hund's rule. So first we have completely, we have put 1 electron each in all the orbitals, and next we have put the 4th electron in the first orbital. So the electronic configuration becomes 1s, as there are 2 electrons in 1s orbitals, so 1s2. Now 2s, again there are 2 electrons in 2s orbitals, 2s2, and as there are 4 electrons in 2p orbital, so 2p4. So the electronic configuration becomes 1s2, 2s2, 2p4. So we just write the shell number, the subshell name, and the number of electrons in that subshell. Now let's discuss electronic configuration of another element, and that is zinc, and it has 30 electrons. So as there are more number of electrons, so this time I will not be drawing the diagram of all the orbitals. We will just be representing it through the notation. So first we will fill the electrons in 1s orbital, and as it has capacity of 2 electrons, so 1s2. Next we will fill in 2s orbital, that again it has capacity of 2 electrons, so 2s2. Next we will fill in 2p orbital, and that has capacity of 6, so 2p6. Next in the energy order is 3s orbital with the capacity of 2 electrons. Next is 3p orbital with the capacity of 6 electrons, and so on. So here you can see that till now we have filled 2 plus 2 plus 6 plus 2 plus 6, that is 18 electrons. So still we are left with 12 electrons to fill. So for that we will utilize the next orbital, that is 4s orbital in energy order, and again it has capacity of 2, so 2. Now in the energy order, the next orbital is 3d orbital, and it has capacity of 10 electrons. So here we will write 10. So now we have completely filled all 30 electrons in this orbitals. So you can see that 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 is 30. So this is the final electronic configuration of zinc. So now I am giving you few questions of electronic configuration to practice on your own. So after learning about electronic configuration, let's discuss another very important concept related to it, that is valence electrons. So the electrons in the last shell of an atom are called valence electrons, and during a chemical reaction the valence electrons are those which play the major role. So let's discuss few examples of finding the valence electrons. So here we are given few elements, and we have to find the number of valence electrons in each one of them. The first is magnesium. So first we will write the electronic configuration of magnesium. So it will be 1s2, 2s2, 2p6, 3s2. So you can see that the last shell in magnesium is the third shell. So the number of valence electrons will be 2, because there is 3s2. This means the number of electrons in the third shell is 2. And let's take another example, that is argon. Its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So in this you can see that there are 2 subshells in the third shell, that is 3s2 and 3p6. So it will become that the total number of valence electrons are 2 plus 6, that are 8. So So in this way you can see that the number of electrons in the last shell of an atom are called valence electrons. So in this similar way, we can write the electronic configuration of all the other elements. But there are few exceptions. So the first exception is chromium, and it has 24 electrons. So first let's write what is the expected configuration of chromium according to the rules which we have read till now. So expected configuration. So for that, first we will fill the s orbital, 1s orbital, then 2s orbital, then 2p orbital, then 3s orbital, then 3p orbital. Now there is a confusion. So till now we have filled 18 electrons. So we are left with 6 electrons. 6 electrons are left. So according to the rule, first they should go in the 4s orbital. But this does not happen. So according to the rule, the expected configuration should be 4s2 and then 3d4. But this does not happen. This is wrong. So what is the actual configuration of chromium? That is actual configuration. The starting will remain same, 1s2, 2s2, 2p6, 3s2, 3p6, but after that, instead of filling the 4s orbital, we first fill the 3d orbital. In 3d there are 5 electrons, and in 4s we just place 1 electron. So according to the rule, the 4s orbital should be filled first. It should have 2 electrons, then 3d will have 4 electrons, but this does not happen. First 3d is filled, so this is the actual configuration of chromium. So in this way, chromium is an exception. Now here we have another exception, and that is copper. It has 29 electrons. So first let's write the expected configuration of copper. So that will be 1s2, 2s2, 2p6, 3s2, 3p6, and now first the 4s orbital will be filled, and then the 3d orbital will be filled with 9 electrons. So you can see that there are 29 electrons. You can calculate them and you can find out. But this does not happen. Again, this is an exception. This is wrong. So the actual configuration, this will remain same. This will remain same, but the change will be here. So again, the 3d orbital will be filled first and 4s will be filled afterwards. So 3d 10 will be there and 4s 1 will be there. Now let's see what is the reason that first we are filling the d shell first and the 4s afterwards. So let's see the reason that why copper and chromium don't follow the rules. So this is because fully filled orbitals or half filled orbitals have extra stability and lower energy. So that the reason that copper and chromium first fill their 3d orbital is that this provides more stability to them. So as you know that 3d orbital has maximum capacity of 10 electrons. So when chromium goes into 3d5 configuration, this means that half of 3d orbital is getting filled. And similarly, when copper goes into 3d10 configuration, it means that the entire 3d orbital is getting filled. And fully filled or half filled orbitals provide more stability and have lower energy. So that's why 3d orbital is filled first, and after that 4s orbital is filled. So with this, we come to the end of the chapter Structure of Atom. Do subscribe to the channel and like the video. If you have any doubt, then ask in the comment box.